Welcome to Advanced Electrical Networks. This is lecture 7. So, in the last class, we saw another perspective of reciprocity, and the basic idea was the following. So, we have, when we write the modified nodal equation analysis MNA equations, we basically have an equation of the a system of equations of the form G sub A times V equals I sub S, where Ga is the augmented conductance matrix, V is the vector of unknowns, which will consist of all the node voltages as well as the currents flowing through the through any of the voltage sources inside the network, and the vector on the right hand side is simply the source vector, which consists of all the independent sources, namely current sources and voltage sources. And we saw that well, when we try to work with reciprocity, one way of looking at it is to basically, we saw that for the case of a current excitation and a voltage output, I believe. And what we do is simply recognize that when we write these equations, what we are doing is injecting a current into node 1. So, this I s simply becomes I in times 1 followed by all zeros, and V o is simply a row vector which is 0, 1, minus 1, all zeros multiplied by V, right, and V is nothing but G A inverse times I s, right. So, V o therefore can be written as 0, 1, minus 1, all the way times 0 times G A inverse times I s, which is V o by I in is nothing but 1, 0, etc. All right. So, this is the corresponds to the input vector. This is the circuit matrix, of course, and this is the what I will loosely call the measurement vector or the measurement matrix, if you like. Okay. So, this you can think of this as a as a mathematical operation, right. So, you have the input, okay, it gets multiplied by a matrix G A inverse, okay, and produces an output which is the input times a G A inverse, and then what is happening? You multiplying this by the measurement vector. So, this is and this is the out, okay. And if you think of this as X transpose, right. So, this I am going to call X transpose simply because it is a row vector, right. So, X is a column vector and X transpose is that is the measurement matrix. This times G A inverse times the input, which I am going to call the y vector. So, the scalar VO by IN is of the form G transpose, I mean X transpose times G inverse times Y, and you know, and remember that if you have two vectors, if you have two column vectors with the same length, let's say I am going to use A and B, what is the dot product of the two vectors? The dot product is nothing but this A dot B is nothing but A transpose B, correct? And you look at this here, and this is the notation for dot product. So, how can you write this as? This is nothing but X comma GA inverse times Y, all right. Does it make sense, people? All right. And so, you can so you can think of it as the following. You have a vector y, right, on which the matrix GA inverse is operating, and the result is another vector, okay, and you are finding the dot product of that vector GA inverse times I with X, right. X corresponds to the measurement, Y corresponds to the input, all right. Now, in mathematics, it turns out that, I mean, a legitimate question you can ask is the following. I am taking a vector y, operating on it, and taking the dot product of the result with the vector x, right, to get a scalar, correct? A legitimate question I can ask is, if I wanted to get the same scalar, but I wanted to operate on x instead rather than y, what should I have done to x to get the same scalar? Does it make sense? In other words, what should I do to x, okay, before dotting it with y to get the same answer as I would get if I Is this clear, people? Right? I mean, this is simply a mathematical question. There's nothing, I mean, why are we doing it? No, this is what the math guys love to do, right? And it seems like a legitimate question, right? Okay. So, you're messing with y first in this computation, you're messing with y, right? And then taking the result and finding the dot product with x, right? A reasonable question to ask is, well, if I messed with x instead, okay, and then computed its dot product with y, I mean, what should I have done to x to get the same dot product? Okay. So, with what matrix should I multiply it to get the same dot product, right? So, so how do we solve this problem, and what do you do, and how can we figure this out? Well, this, whatever operation you do to x, the whole, I mean, that's clearly, let's call that, I don't know, I mean, I'm going to call that G star, right? So, x transpose times, what is this guy? G star times x transpose times y should be equal to x transpose GA inverse times y, all right, okay. And this is nothing but x transpose G star transpose y must be equal to x transpose GA inverse times y. So, what comment can we make about G star? GA transpose inverse or inverse transpose, it does not matter. Okay. So, in mathematics this G star is called the adjoint operator. All right. And you can see that what this is telling us is that what is this telling us? If we want the same transfer function, right, another way of interpreting this is to say, well, VO by In we know is X transpose GA inverse times Y, okay, which can be thought of as, let us call this, I mean, remember this, in other words, when you write an expression GA times V equals IS, how do you, I mean, this is mathematically this is a set of equations, but how would you interpret this? These are nothing but the node voltages that develop when you take a network with an MNA matrix G and have a source vector IS. That is the interpretation of this set of equations as far as we are concerned, correct? Okay. So, when we have multiple input sources, as we were discussing yesterday, right, to do this by superposition is equivalent to finding GA inverse times IS for each source separately. So, in effect what we are doing is computing the inverse multiple times. An alternate way of doing this and a smarter way of doing this is to basically say, well, we know that V out by I in is X transpose times GA inverse times Y. Remember, X is the measurement vector and Y is the excitation vector or the input vector, correct? So, you can think, I mean, what comment can we make about the dimensions of that guy there? Let us say there are n unknowns, let us say X, Y are both n cross 1 vectors, because there are n number of unknowns, and GA inverse, what is the size of that? N cross n. So, what comment can we make about X transpose times GA inverse? 1 cross, it is a row vector, correct? And I am going to call that V hat, all right. I mean, it is just notation, there is nothing holy about that, okay. So, basically this is saying X transpose GA inverse equal to V hat, I mean, let me call that V hat transpose, because V hat is, I would like to call all my vectors to be column vectors. So, X transpose GA inverse is a row vector, okay, and if V hat is a column vector, then it must follow that I can write X transpose GA inverse as V hat transpose, right, which is equivalent to saying, what does this mean? X transpose is GA times V hat transpose, which is equivalent to saying X equals what? Pardon? Hold on, I think I am at X transpose GA inverse equals V hat transpose. V hat is basically a column vector. So, what do you, pardon? Oh, sorry, yeah, sorry, thank you. So, is V hat transpose times G A must come on the right hand side, and therefore, X must be equal to G A transpose times V hat, correct? Or in other words, G A transpose times V hat equals X. And remember, what is X? What does this denote? What did it denote in our, this is the measurement vector. That was the name we gave to X, or so, but how do you interpret these equations? This, when we said G A times V equals I S, how did we interpret that? What is the interpretation of this system of equations? In English, how would you describe that? Right. So, V is, I mean, in English, what this means is that V is the vector of node voltages produced when you excite a network GA with IS, correct? Now, by the same token, what comment can you, how can you interpret this? Yes. What are we exciting with X? Yeah. So, basically now we have, how do you, the interpretation of this is that we are now exciting a network with whose MNA matrix is GA transpose with X, which corresponds to the measurement vector, right? So, earlier wherever you were measuring, now you have to excite, all right, and the voltages that are developed on this network are V hat, all right, okay. And once we find V hat, to find the individual transfer functions is simply from the multiple inputs is simply multiplying people. Once you find V hat, what do you do? Yeah, so basically remember that in the original network, V out is basically what do we call that? X transpose times GA inverse times GA inverse times Y. And what is X transpose times GA inverse? What is it? V hat transpose, okay, all right. So, and once we have V hat transpose, finding the various transfer functions from multiple inputs is simply a matter of multiplying V hat transpose with whatever input you want, correct? So, in other words, V hat transpose, that matrix, that row vector, contains information with regard to all the transfer functions, I mean the transfer functions from all the inputs to a given output, right? And this Y merely selects which of those transfer functions you want, that's all right, okay. And so therefore, if you want multiple transfer functions to the same output, this obviously entails a lot less labor, because you're solving, and how do we obtain V hat? We just solve not the same network, but a related network, where what is the relationship between that network and the original network? The MNA matrix of the modified network is simply the transpose of that of the original network, okay. So, we form a network whose MNA matrix is the transpose of the original network. That's what's called what's that called? if you have a network whose MNA matrix is the transpose of the original network, what is that called? What do you call that network? Yeah, it's that's called either the interreciprocal network or the adjoint network. All right. Is that clear? So, this equation in mathematics is often called the adjoint equation. And so, the bottom line therefore is that interreciprocity can be simply thought of as evaluating the first two terms of this equation, rather than if we did superposition, we would be evaluating that product first and then dotting it with X transpose. It does not make sense because that output vector is not changing, it is only the input vector that is changing. So, it makes sense to compute the stuff that is not changing, right, okay, because that G inverse is difficult. So, it makes sense to compute that X transpose GA inverse once, okay, and then as you keep changing the input sources, the Y will keep changing. So, the finding all the transfer functions are easy. Does it make sense, people?